Today, I'm going to first tell you a couple of minutes what we're about and what's my background, and then I will take you into the mysterious world of data science that's related to typical traffic analyses. Our company is already quite a bit through its merit basis, so we also are mainly an affiliation of TNO, which is a Dutch research institute, so the two combined parties, they established what the spin-off company is. In contrast to what many people think, we are not subsidized, so we have to find our own money, bid for tenders and everything. We do have subsidies, but those we have to earn, like for IWT, for example, or the European Commission. The very interesting part is that everything that we do is open, so you can go to our website and nearly all the reports are available. So if you do a study for someone, it's typically in, let's say, 90% of the cases fully available with all the details and the scientific methodology behind it. And this is very, let's say, it's welcomed because most of our competitors don't do that kind of thing. And it is not that we lose business secrets or anything, because this is generally well-established methodology that it's about. And the most important thing that you need to understand about what we do or why we do it is this in bold impact assessment. The question is always, you have a policymaker, he has a certain question, we try to devise models, we use these models, calibrate them, and then we can make an educated result. It's not just about saying how much or how much better it is, but really quantitative numbers. So this is why we are really into data. Sometimes we also do stuff, but that's more of our personal nature, because there is data available. Sometimes the question isn't always clear, but there is data, and by looking at the data, you see a whole lot of possibilities exploding, and this is one of the things that I will show you today. Another thing is that we are very regularly featured in the press, so anything related when, for example, a truck on the ring road around Brussels loses some of its cargo and it has a jam as a consequence, then they sometimes call us to ask, how much does this cost to society, based on the time that everybody loses? And these are one of the things that we are quite fluent nowadays in order to answer them. Within our company, since let's say a couple of years, 3-4 years now, we established what we call the data enrichment group. And the background is typically, companies have a lot of data, but they don't always know what's the potential of this data. Take, for example, we had Toyota. They had a lot of data of cars that they tracked every 20 seconds or something. We looked at the data and we looked at what the value business proposal would be for them and what they would get out of it. And the interesting part is that by looking at one data set alone, that's interesting, but that's not as nearly as interesting as if you combine data sets. Now, I don't need to tell you about data fusion and stuff like that, but we're talking about very different types of data sets. And nearly all the problems that we need to tackle involve various kinds of data sets that need to be involved here. As an example of some of the things that we calculated is, what's the amount of congestion? Based on what let's say the traffic detectors in the road concrete, what they detect, the number of vehicles, the speed at which they pass, we can establish a relation between the number of vehicles passing by and the speed that they're passing by. And if you have the speed, then you also have the travel time. And you can use this to compare the typical travel time in a morning congestion hour to, let's say, the travel time at night when there is no congestion. And you can have this offset. And this offset gives you an indication of the time people lose. That's one part of the equation. The other part is, how much does this cost to society? Every one of us, let's say, if I ask you how much are you willing to pay in order to be 1 hour earlier at your work, or how much are you willing to pay for public transport in order to be 1 hour earlier on your work with respect to congestion, let's say for typical work-related commuting, that would be around 10 euro. For trucks, it's about 35 euro. It's the cost of the pay cost, the wage of the truck driver, the cost that whatever he is carrying in his truck is not in the store, but is still on the road and as such has no economic value. These things we can use to calculate what the total amount of money is that we would all lose when we are stuck 1 hour in congestion. So the equation then is fairly simple. You just figure out how much time do we all lose, with how many people are we, and what is the composition of traffic, trucks versus cars, let's say. And if we make a calculation about this, it's about 600,000 euro per day. In economical terms, this is an opportunity cost. So this is what we are all willing to pay. The concept behind it is quite economical, but giving it a number makes it very tangible. And another interesting part is that if you look at congestion, most of the time when you hear about congestion, it's always on motorways. That is because motorways are sexy. Everybody knows the E40, the ring road around Brussels. No one knows about some local road near my village, for example, which is always congested. And I live in Kruisalten, which is away from where civilization actually started. So the thing is, it's only what is reported on the main motorway network. But that does not mean that we should neglect what happens on the underlying road network. And there it appears that, let's say, the time we lose there is almost 4 times as much as we lose typically on the main road network. This is actually a message that we want to get across to policymakers, in that they also have to look at measures for, let's say, optimizing traffic flows on the more local routes. Of course, Wallonia, they also wanted to have a bit of congestion, but it turns out that given the amount of congestion on the various motorways and given the amount of motorways within each of the regions, over 90% of it is located in Flanders. Now, where did this all come from? Before traffic flow theories and everything, there was a guy called Greenshields, and in 1935 he stood with his camera looking at a piece of road, and he figured out, there are people driving here. So if there are not many people, then we go to the left of the graph, then they drive quite fast, so speed in miles per hour is between 40 and 50 miles per hour. But as more and more people enter the road, traffic seems to slow down a bit. So we established a linear relation between them. And this is the basis from all traffic science that you know today in the world. Interestingly, this is a data set of around, I think, 10 or 11 data points. All of these points were gathered in the left upper corner, where you can see a small cluster of non-congested traffic. And then on a completely different day, on a completely different road, he figured out another point, which is in the lower right corner. So you could say these are not even the same samples, but yet he combined them, and we didn't care. We have a traffic flow relation. And this linear relation is what we call the fundamental diagram of traffic flow theory. And it's based on these kinds of measurements. Now, a while ago they celebrated this, the 75th birthday of it, and if you go and measure what you see on the road, this is for example what is measured on the E17 in the direction of Antwerp. Horizontally you have what we call density. It just shows you how many vehicles are there on a kilometer. So if your road looks like a parking space, then it's very crowded. On the other hand, if there are not many vehicles that you count per kilometer, then it's not very dense, the traffic. On the other hand, if you look at traffic and you see them passing by, for you it's like this, so they're driving by, and the faster they drive by, you see more and more vehicles passing by. But then there comes a point where congestion occurs, and you suddenly see a lot of cars, but they're driving more slowly. This point is located near the top of this, what we may call graph. Of course, this is what we truly measure. If we look at the graph, the assumption that we make based on the relation that you saw before, it looks something like this. But not everybody is convinced that this is the correct shape. Some say it should look like this a bit. Depends on where you want to, let's say, put the clustering. If you cluster the data in 2 separate groups, well, you get one good group and then everything else. That's a typical problem. There are also German people who believe that this is completely wrong to have such a simple structure. It should at least be something like this with inflection points and everything, which cause a lot of problems in certain traffic flow models. These traffic flow models are based on partial differential equations, and depending on the type of function that you use here, you sometimes get vehicles that are driving backwards if you don't correct for these kinds of things. But we've been through all that. Ever since 2002, I guess, they solved most of the problems there. But it has been an interesting time before that. But it goes even further. Because if you look at traffic, what you see is that it goes, many more vehicles drive by, it goes very fluently, and suddenly, bam, everything stops. The reason is that when we drive closer to each other, given our reaction time, we can let go. For example, if the guy in front of you has his red lights, his stopping lights on, you don't necessarily need to brake. It might be a small disturbance, but as the disturbance gets larger, the effect grows. We talk about asymptotic instability. The problem there is that at one point the chain might break. If the chain breaks, we have congestion. And this is like a 0-1 event. It goes from no congestion to bam, congestion. But on the other hand, if you look at traffic going fluent again, it doesn't go from 1 to 0 again. It goes intermediate. We call this the hysteresis phenomenon in traffic flow. And there are a lot of discussions about what is needed here. For example, if you have congestion on a road and you want to resolve the congestion, that means that a lot less vehicles have to be there. The traffic jams have to have the time to be able to dissolve. Now, depending on which school of thought you abide by, some people say this is not actual reality. It depends on how you measure traffic flows. It depends on, do you measure stationary things like you measure congestion, or you measure free flow, but you do not measure like vehicles accelerating out of a congestion, for example. Depending on what you have there, your curve looks different because your point cloud looks different. So the sampling is very important here in order to define what you want or what you don't want. This is mainly a matter of belief in many cases, and in that respect we are still not out of the woods yet. So these were the first measurements. If we look at what's in reality, there was a company, Traficol, in the west of Flanders based, and they've been bought by FLIR. They create cameras. They don't create cameras, they create software that drives the camera, and they look at the image of a road, and they look at the gray background, they subtract the background, and based on the, let's say, the image processing, they can figure out, is there a vehicle or not? Based on these cameras, you can quickly estimate the number of vehicles driving by. Now we know that these cameras are not really perfect, so people, and especially the government, tends to rely on what we see on the upper right, double loop detectors. They're just two wires of copper, let's say, and they're energized. And anytime a vehicle, if you energize the copper wire, you get a magnetic field. And anytime a vehicle passes over these copper loops, let's say, the magnetic field changes because of the ion content within the car. And because of the change, you can detect it, and then you can calibrate these curves to figure out when did the vehicle pass the first curve and the second curve. So you can establish the speed and the time at which the vehicle passed by. You can also establish the length. And now in Flanders, they have the motorway network completely figured out. With every 500 meters, there are a couple of these things that you see in the road, and they measure up to 4 types of vehicles, and they combine them every minute. So every minute you get measurements from the speed, the amount of vehicles, and the class of vehicles. You can also work with lasers or anything. This is what, for example, the police use in order to establish when you are speeding, and that is based on the Doppler effect. These are the typical ways to gather classic traffic flow information. Once you have it, and this is some of the stuff that I played around with in my PhD and that everybody should play around with when you start with these things, you can just visualize them. And you typically see Monday, Tuesday until Friday, and then you have a Saturday and a Sunday, and you then see also very interestingly that on a Sunday, traffic gradually increases towards the night. This has to do with the fact that there's a lot of night traffic visiting people. If you go to look at the motorways near Leuven, you see a lot of student traffic, let's say, or students that have to come to Leuven. You also see that on Saturday, there's also traffic, but a bit less, and there's no morning congestion, luckily for us. If you were to cluster this, it would easily give you these type of clusters. And it goes even further. We looked at data from a whole array of detectors. We saw what was in the data, and then we let all the clustering methods that we knew loose on this, and this way we could figure out what is the optimal way to cluster this kind of traffic flow data. And I think this is based on a time aggregation of 5 minutes. So every 5 minutes you have a new measurement of the total amount of vehicles and the speed at which they're driving. And you can use this information to automatically cluster. What you typically see though is that the weekends are very clearly identifiable, but what happens within weekdays, that's a bit more difficult. So there might be other types of measurements that you need in order to differentiate what is going on a Monday versus a Friday. Typically, they say on a Monday, you have a large morning congestion, on a Friday you have a large evening congestion. These are the things that you see, but not based as such on these kind of measurements, but more on measurements of congestion length and stuff like that. Once you have that, you can draw heat maps, and if you look at the center image, you see the ring road around Brussels. Suppose I take this road and I stretch it, then instead of vehicles driving around the ring, they're driving from bottom to top. And what we do is we set time on the horizontal axis. So vehicles drive from the bottom to the top, and they drive from the left to the right. And what you see is that this bluish, that's the speed. They drive at a very high speed, which is logical because at, let's say, 10 or 12 o'clock, there normally isn't any congestion. But these highlighted areas, these, let's say, yellow spots, they indicate lower speeds. And so we can use these kinds of measurements of more than one detector to figure out where is the congestion located in time and space. These are hence called time-space diagrams, and they're the basic tool to understand what is going on within traffic flows, let's say from a dynamic point of view. And then we can go on. We can calculate, as I told you earlier, the amount of time we lose. For example, the curve you see horizontally is the amount of vehicles that drive past a certain point, or in total, let's say, and vertically is the travel time they need. And to the left, we have this black cloud. That's typical nighttime traffic. Not much traffic, with a quite low travel time. But as you enter the morning congestion, I think it's these blue dots upper right, you see that there are a lot of more vehicles driving by, and they're driving at a much higher travel time. And what we then do is we draw this curve in between, and we say, well, this is our model. We can then say, give me any amount of vehicles, and we'll tell you what the travel time is. And this is then used in various studies all around the world, and the clue is to have these things calibrated. But you can immediately see that calibration here is of course not that easy. Where do you put, on the left side it's easy, but to the right, do you put it higher, lower? We are now underestimating the morning congestion and a bit overestimating the evening congestion. So this is not even a true curve that you can use to distinguish between the morning and the evening rush hour. But it might be useful if you look at a year traffic, all traffic in 1 year, then you may use such aggregate measures, let's say. To the right, we have another interesting curve. Suppose you live in Brussels, suppose you live in Leuven and you work in Brussels, then every morning you have to go through congestion and in the evening back again. So one of the things we did was, how much time do you spend in your car in a jam? And it appears that people doing that, living in Leuven, working in Brussels, are worse off. Half of their time in their car, they're stuck in congestion. But because the trip is not that big, the time they lose is not as much. So on the other trajectories where the travel time is longer, you spend a lot more time. But relatively seen, you spend less time in congestion. This is something that indicates where the, let's say, the potential bottlenecks are and where people need to take action. Look at average speed control. Your license plate is scanned at the E40 near Aalst, Erpenmeren actually, and it's scanned again near Wetteren. And based on the time difference and a match in the database, they calculate the travel time you had. And based on the travel time, you can know, is the guy speeding or not? And one of the things we figured out with data, very fine data, 2 years of data, every 5 minutes, all the speeds and all the amounts of the numbers of vehicles, we could clearly see that once the average speed control was in effect, we saw that the number of violations typically dropped. So depending on how fast you are speeding, you get a light violation, minor violation, or you get a real speeding ticket. And you still see, interestingly, that some people still persist, which is good for the income of the Belgian government. On the other hand, it's not good for them because they get busted each time. Of course, all this data is only as good as we think it is. So if we look at the quality of the data, there are huge differences. This is just an idea. All the traffic detectors are lined up horizontally, and every day in the year is put vertically. And depending on the color, you have a problem. So if there are black lines, that means black vertical lines, that means that all traffic detectors had a problem in that day of the year, which is very unlikely. So there's probably a problem within the database itself. Now, if you looked at the data, I saw that the data was getting progressively worse from 2001 to 2005. But then they started switching to double loop detectors. Remember that Belgium originally had single loop detectors, which is old technology and not good at all, and they make huge estimations that you won't even dream about to put into a model. But the data was getting worse and worse, and they were also not, let's say, helping in that sense. So they decided to install new detectors. So this quality control is now very important. Within the government, they have a very dedicated group only looking at, is our data good enough? And if you ask them, it's not good enough in order to share it, but we as data enthusiasts, we believe just share it and we'll do the data cleansing or we'll look at what is necessary in that case. Remembering Bartemore, our previous professor, he always said reality is just another model. Did you know he was right? Depending on what you put in your model, what kind of data, you get certain results. Do not just believe the models, especially traffic flow models that are being used to calculate whether or not the Oosterweel should be closed or not. Will there be congestion on the ring road around Antwerp? Well, all these kinds of models, they're typically wrong because the data underlying them is not correctly used, the calibration is faulty, the model just makes the wrong assumptions about reality, so you have to be very careful when interpreting these results. Now, today is also not just about data, but it's about getting really big data. There were the days when we wrote a proposal, we had to put the word sustainable in it. So if your project had the title sustainable, you got funded because sustainability is important. That has changed a bit. Now you do not need to be sustainable anymore. You need to be smart. Yeah? Smart cities, smart traffic, smart planet, everything like that. And so the next trend now is getting this big data involved, crowdsourcing, stuff like that. So we're actually in a trend that is growing and growing, and where more communities are participating. If you want data, well, there is data, big data, but traffic typically at the moment is not big enough. If you want to have really big data, then you should go to CERN, or you should go to the data coming out of a Boeing 747. In one flight, it has more data than what we gather in 1 year of traffic flow data, for example, for the entirety of Belgium. So it's a bit relative. But things are changing depending on what kind of measurements you are looking at. For example, if you look at people driving, these are all employees from Toyota, and we follow them every 20 seconds of their life in their car. And we did that for over 1 year. There were about 300 people, and you typically see how the morning peak arises and where they are driving. Of course, Toyota is located within the center of Brussels, near Deze, more on the side actually. So we saw how people are driving by. We see where typical bottlenecks occur because we see their speeds dropping. For example, this is the ring road around Brussels. The bluish color is the high speed, around 120 kilometers an hour. But the more the redder come, the more the color turns red, the more congestion sets in. And this is quite detailed data because we followed everybody every 20 seconds. I knew that when they were parking in the evening, they always parked in the vicinity of their house. Not exactly at the same spot, but you can draw a correlation between all these clusters of data points. And then you can easily pinpoint where the people are living or where they are working. And this is very insightful, not from a, let's say, privacy perspective, but more from what is going on. How are people behaving on the roads? How is our mobility behavior? And for that, this is quite interesting. It goes even further. Suppose that we all stop using the car and we switch to public transport, then there's a problem because we created a model, and the model said, okay, let's now, knowing that someone goes first from here to here, and then from here to here, and then to here to here. So you drop off kids, you go to your work, you go to the store, pick up kids, and go back home. These trips, if you want to do them by public transport, you have to take into account that you have to have transitions, you have travel time, you have connections, things like that. It's not always possible. So depending on the scenario that you have, optimistic or realistic, we see that only 1 in 12 trips can be replaced. So the 8% means that of all our journeys that we do on a daily basis, only 1 out of 8 can be, let's say, switched to public transport as it is today. The lesson here is that we should not only invest in public transport and change that, but also that we have to change our mobility behavior. If you step away from the car, you cannot just be anywhere, anytime. You can't even do that nowadays, and there are a lot of other things that you can do. And the really big data comes from, for example, these green clouds. Those are all the Twitter feeds that you get at one point in time. Then you see where all the people are. You see how they are moving, so you can all follow this. We have Bluetooth scanners. You can do anything with that. They use it for cars. They use it also at festivals to detect pedestrian movements. Are people crowded at, let's say, the main stage, or are they going to the rest, what's called the bars or stuff like that? You can all get this from the data, and this is the really big data because there's quite a lot of it. And of course, we are moving further and further. In your car, there is something called the CAN bus. It's a standard, and everything that your car does is put on this bus. Bus means a communication channel, like in the early PC. And what you get is that if you steer to the left, the amount of steering is also put on the CAN bus and it's logged. And you can buy a simple Bluetooth transponder from, let's say, China, put it in your car, connect it to your tablet, and then you in real time see what is going on. There's of course standards and everything, but it also allows us to figure out how is your acceleration behavior. So we can pinpoint when people are not eco-friendly driving, when you are overdoing it. If you're continuously hitting the gas pedal, if you're always braking instead of coasting, things like that, your fuel consumption rises, and we can learn techniques in order to have a lower fuel consumption and a more economically viable trip, let's say. And this is based on this kind of detailed data. Going even further, this was let's say a side effect of one of the experiments we did. We figured out where people were driving in Leuven, and you can see where we have a zone 30, what is going on within the zone 30. I also saw people speeding within this zone 30, individual people. So this is actually very interesting data to, let's say, sell to the police, in the sense that they can now figure out where the hotspots are, where traffic is more unsafe than other locations. What they typically do in Belgium is to figure out where we are all going is they ask us. They just ask, let's say, in a census of 1,000 people, where do you work, where do you live, how many times a day do you use a car, for how many trips, what's the typical distance, blah, 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 blah. Just follow these people within their car, log everything, and you get all these questions answered automatically purely from the data, and much more than you would originally have. So this is why these travel patterns are actually buried within the data, but you can easily get them out, given that you have the data. For example, we did an experiment with road user charging. It's high on the agenda from time to time, depending on the type of government you have. We did an experiment between Brussels and Leuven, and we saw that people changed their behavior. So they got this small onboard unit in their car. It measured their position. It also told them, if you drive on the motorway in the morning congestion, this is the amount you will have to pay per kilometer. Or vice versa, if you drive on a local road or in a city in the low hours or in the peak hours, this is the amount you have to pay. And the idea there was that they will be incentivized to spend less money. So money is there, the incentive, in order to change people's behavior. And what we saw from the data from our test participants is that they drove less in the morning. So the blue curve is before, and the red curve is after the kilometer charge was put in place. And we see that people actually drive for lower costs. They drive also more during the day, and they drive a bit later in the evening. Of course, this is a small sample, and the people were willing to participate in our experiment, so it's a bit biased. But this is why the government made a new effort in order to have, I think, around 1,000 people followed within their car, but the results aren't nearly as satisfying as these are. And from what a little bird told me is that they will continue with the experiment until they get the answer that they're actually seeking, which is also interesting, because then as long as they're tendering, we are happy to bid. We also have parking management. This is the next big thing. You can just look at parking spaces in garages. They can have detectors in place to tell you there are this many vehicles within the parking garage, or there are this many parking spaces left. Or we can shift and we can say, we look at every SMS that is being sent in SMS parking, and we can just look when in time are these SMSs occurring. Then we fit a statistical model on top of this, and then we can say with, let's say, 95% probability that you will have a parking space within the center of Leuven at around 12:05, depending on the data that you get from this. This is quite interesting, and it doesn't need very detailed sensors in the concrete or anything. You can just do this with existing data. More or less concluding, what you also have is potential for electrical vehicles. Now, an electrical vehicle is quite expensive, so the question is, should the government change its fleet park and electrify everything? Then the question becomes, given that an electrical vehicle needs to be charged and has a finite action range, it can drive, let's say, 400 kilometers and then it has to charge for 2 to 8 hours, it depends on your behavior. Are you someone who makes a lot of small trips? Do you make a lot of long trips? Do you make less small trips, etc., etc.? And depending on the behavior that we see, we can figure out, well, this is the zone in which there is enough space, there's enough time for the battery to charge, and the distance is small enough so that it fits within one battery cycle. And based on this, you can make an educated guess on whether or not your fleet can be electrified given its usage, which is a very important parameter here. And nowadays, we are involved in anything related to autonomous vehicles. If you thought you had a lot of data, then these things, they can do a lot more. For example, when we see a traffic situation, we scan it 1 second, 1.5 seconds. These kinds of things, they measure with their LiDAR detector, they measure every 1,000th of a second, for example, the entire vicinity, and everything is logged. And this goes really, really far. And what we are now doing in a project with Flanders Make is developing a self-driving bus. It will go very slowly in the beginning. These things typically drive 20, 30 kilometers an hour. But we are going to figure out what are the typical traffic safety interactions that people encounter. What if children jump in front of the bus? How does the bus detect this? What will be the consequence? And of course, all the ethical questions related to, which has been in the news, for example, should your autonomous vehicle drive straight onto a group of 10 children crossing the pedestrian walkway, or should you smack your vehicle into the car and kill the driver in order to save these 10 children? Ethical issues, they're all abound. And I think this fits in well with the previous presentation in a sense. There is a lot of new route planners coming into play, and we see a trend. The trend is not just to have multimodality per se, but also to have all the ticketing involved. So I want the route planner to know and to tell me the amount of tickets I need in order to take the bus or the train or to have a connection. I will also buy them from my smartphone, and I will also validate them on the bus via NFC communication, for example, via the chip within my smartphone. And this is the thing that is going on nowadays more and more. And of course, where would we be without at least the ethics behind all this data? I told you already about where the people live and stuff like that. In road user charging in the Netherlands, they are typically always a bit ahead of us. What they originally said, like either you have this onboard unit that transmits all the information to a backend server where it's aggregated, or all the calculations are done within the onboard unit and they never leave. The personal data never leaves the car. They're two different things, different costs as well. And in the Netherlands, they decided in the end to have every calculation being done within the vehicle so that sensitive personal data is not exiting and being stored in another database. It depends on where you want to put the focus. But here there are a lot of techniques. People are now talking about privacy by design. So during the construction of, let's say, the chain of where data goes, they already put, let's say, guarantees in place that data cannot be just combined or reused or whatever. They have obfuscation techniques, things like that, encryption, of course, so this is very important. And the point is, there's a difference, because this is something I also want to say. Privacy is what you allow people to do with your data. Security is how the data is actually being transmitted and secured in a sense. They're two different issues. In 9 times out of 10 when people have a problem with the privacy, they actually have a problem with the security. The privacy is quite okay in that sense. And what we see nowadays is that all data is being opened up. This is not just of goodwill, it is actually mandatory, required by the government, by the European Commission. There are a lot of these directives, for example, the PSI directive requiring all our public transport operators to release their data, which is not always easy because we also work for Infrabel, for example, and they have a lot of data sets in there, and opening them up, that's not never going to be the case. But there are a lot of interesting cases where this might be useful. And if you go one step further, smaller cities, or also even Brussels, they're opening up their data. They're organizing hackathons. They put the data sets online, like these are the real-time parking space occupancies. So we know at every parking garage in Ghent, the amount of vehicles at any time of the day, real time. Do something with it, make an app, make it useful for society, and then we see society entering the picture and also making sure that these apps are really being used and they are reshared and rebuilt and everything. And this is going quite far. And this is more or less the future for this data, in the sense that there's a lot of data now, and we have these, let's say, crowdsourcing more or less, and these crowds that are also entering the, let's say, the field. And they provide a lot of new information to cities or to local governments. So if you have questions, we'll talk now. And you can always visit our website and get more insight into everything. Thank you.